Did you ever stop to wonder why it is that things seem to fall toward the earth? That's what Bob did one Saturday, resting after a game of touch football and watching the autumn leaves drifting down from the trees. Almost everywhere you look, you can see examples of the downward pulling force known as gravity. Gravity pulls children down the slide in the playground. Gravity pulls down on a ball all the time. Even though you can kick the ball high into the air, gravity keeps pulling and brings the ball back down. What is this thing called gravity? It even holds Bob down. And airplanes have to use power to stay in the air against gravity. Bob was wondering what would happen if there were no gravity. And that's where I came in. I know Bob. I'm an engineer at the same plant as his dad. So he asked me what I could tell him about why things seem to fall toward the earth. Well, I was on my way down to the plant. I suggested Bob come along. We'd see what we could work out together. Gravity is so common that many people don't even stop to think about it. Our bodies and things all around us are held to the earth. Yet there is more to gravity than that, I explained to Bob. To appreciate gravity, you must understand what Sir Isaac Newton meant when he formulated the law of gravitation. As it's sometimes expressed, mutual attraction exists between all bodies. Those are big words for a big idea. But gravity's mutual attraction between bodies is something like the magnetic attraction between two magnets. Each is attracted to the other. That's what we mean when we say that the attraction is mutual. And just as in magnetism, where a larger, heavier magnet can have a greater attraction or pull, so in gravity, the heavier the bodies, the greater the gravitational pull. Bob could understand mutual attraction between magnets, but was there any mutual attraction between him and that desk, for instance? Well, that attraction is very small, but it does exist. We engineers know that it does because we've measured the attraction with delicate instruments. You measure gravity's attraction every time you weigh something. Now, the Earth has a mass billions of times as much as Bob, so it attracts him with considerable force. We measure that force to be 120 pounds. And because my mass is greater than Bob's, 164 pounds is the measure of the mutual attraction between me and the Earth. How does this attraction of gravity affect our solar system? Let's look at it in miniature. Suppose the Earth were the size of a grapefruit. At the same scale, the moon would be about the size of a golf ball. And they would be about 10 feet apart. Nearly a mile away, there would be another round object, say that water tank, about 36 feet in diameter, representing the sun. Mutual attraction keeps these bodies in their places in the solar system. Why don't they come crashing into each other? Well, it might happen if it were not for the fact that all heavenly bodies are traveling through space at tremendous speeds. But the moon, for instance, doesn't go flying off in a straight line because of gravity's mutual attraction between the Earth and the moon, which we can represent by a 10-foot string. Centrifugal force tends to keep the moon going in a straight line, but the force of gravity, represented by the string, pulls it into a circular path or orbit. For exactly the same reasons, the Earth moves around the Sun in its own much larger orbit, pulling the Moon along with it. Bob was worried about something. If gravity's attraction is dependent on mass, then does the little Moon have less attraction than the Sun? I was pleased. Bob was really trying to figure this thing out. He was almost understanding Newton's law of gravitation. Gravity does depend directly on the masses involved. But it's inversely proportional to the distance, to the square of the distance. If two objects are moved twice as far apart, the pull of gravity is 1/4. So there's our Sun, almost 400 times farther from the Earth than the Moon. It all made sense, Bob said. The greater the distance, the less the attraction of gravity. When you understand how the attraction of gravity falls off as the square of the distance, you appreciate how spaceships may travel by rocket to the Moon or to other planets. I've been playing around figuring space travel, and the pull of gravity works like this, I told Bob. Say you're here at the surface of the Earth, 4,000 miles from its center. That's the radius of the Earth, 4,000 miles. You weigh 120 pounds. That's normal here at the surface. But you take off in a spaceship. Now you're out 4,000 miles from the surface, really 8,000 miles from the center of the Earth. Being twice as far from Earth's center cuts the pull of Earth's gravity to 1/4. He'd weigh only 30 pounds. The attraction of gravity is inversely proportional to the square of the distance. And up here you must use rocket force in reverse to overcome the Moon's gravity and prevent a crash. I had some movies there of the first experimental rocket flights. The force of the rocket motor overcomes the force of gravity and slowly lifts the ship. But these early rockets went only about 100 miles up before they ran out of energy, and gravity pulled them back to Earth. So Bob had a better understanding of gravity, the mutual attraction between bodies. And then he said he'd always thought of down as this way. But actually, to a person at this point on the Earth, this way is down. And to a person here, this way is down. This person is not upside down. As long as you're on or near the Earth, down is toward the center of the Earth. This gravity is attracting everything, solid things, liquids, and even gases, the air around us. Every time you lift something, you're working against the pull of gravity. But we put gravity to work, too. We hoist coal into trucks and let gravity pull it down into our basement. And in the furnace, the coal heats the water for our radiators. When the air around is warmed, it expands, becoming lighter than the cold air around it. So gravity pulls the heavier cold air down, forcing the warm air to circulate and heat the entire room. And so it was that the curiosity about leaves falling down from trees led to an understanding of gravity's mutual attraction between bodies and its importance to our solar system and to so many things on Earth. For example, Bob can figure out the part that the force of gravity plays in drinking through a straw. Can you?